So we're going to talk about sine and cosine as periodic functions. So I'm going to explain really everything about these two functions. So first, what is a periodic function? So a periodic function, I'll tell you the formal math definition first. I'll show you what it is. So it's a function where f of x equals f of x plus np for every x in the domain of f, where n is an integer and p is a positive number. Okay, so I can already hear yeah, sure. What? So what does this mean? So this actually does tell us something very useful, but in plain language, a periodic function is just a function with a graph that has a repeatable pattern. And so the way that we represent that is that we write it out like this. This is showing that the pattern repeats. So that's what it means to really be a periodic function. It just has this repeatable pattern. And we can think of functions that would have this. So some examples would be like the way that tides move in and out, or like the phases of the moon. Those are periodic. They repeat, right? Or if you think about what the graph of a heartbeat would look like, that would also be periodic. So they just have this repeating pattern in the graph. Now, in trig, there are two known periodic functions. They are sine and cosine. And so we're going to talk about what these graphs look like. Now, the first thing that I want to do is I just want to talk about like how can we see that they are periodic? We actually can see this from the unit circle. So I want to just kind of think about how these graphs kind of move through the period by looking at the unit circle. So here's my unit circle. And so if you think about as I move from 0 to pi over 2. So I want to just notice the behavior of my coordinates. Okay, so just kind of go with me here. So notice with the y values, so I go 0, 1/2, square root of 2 over 2, square root of 3 over 2, and then 1. So I go from 0 to 1. The y values are increasing, and we know that that represents sine. And then I want to just also note that the x values are decreasing. So the x values start at 1, and they make their way to 0. So, okay, we're just noticing behavior here. So as we move from 0 to pi over 2, sine is increasing from 0 to 1, while cosine is decreasing from 1 to 0. Okay, so let's keep going. So I move to the next part of my unit circle. So notice now that with my y values, so I'm going from 1 to 0. So my y values are decreasing, so sine is decreasing from pi over 2 to pi. And then the x values, so I'm starting here at 0, and then I just get progressively more and more negative. So these continue to decrease. Okay, so we notice then from pi over 2 to pi, so sine is decreasing, as is the value of cosine. So the y values are decreasing, the x values are decreasing. Okay, so next we move on to the next part of this. And so once again, so now I can see I'm going from 0 to -1. So my y values are continuing to decrease. Meanwhile, my x values are going from -1, and then they continue until they get to 0. So the x values are starting to increase. Okay, so I can note those as well. And then I just want to note this one more time, and then you're going to see how this becomes periodic, okay? So just stay with me here. So in this last part of the unit circle, so notice my y values, they're going from -1, and they're increasing to 0. So they're increasing from -1 to 0. Meanwhile, my x values are going from 0, and they're making their way to 1. So the x values are increasing. Okay, so I've noted these behaviors of the coordinates. And so then what ends up happening is what if I did another round of the unit circle? So what if I started the whole thing over again? This is where the period would start over. So if I decided to now do another round around the unit circle, so let's say I've hit 2 pi, and now I'm going to go to, 5 pi over 4 or whatever. If I continued that, this is where the period would kick in. And so then I would be back to my y values are increasing and my x values are decreasing. So that's kind of what makes this periodic. We can continue to go around the unit circle, and we will see this set of behaviors that we just saw. We will see this pattern continue. So I want to view these though without the unit circle. I want to view these on like an XY graph. So we're going to look at each function separately, sine versus cosine. I'm going to show you that in this video. And I just want to make it clear that we're not using the unit circle anymore. So instead of using s's or thetas, I'm going to use sine of x and cosine of x so that you can clearly tell that we're moving into the xy coordinate system. Okay, so I'm going to use the unit circle to help me figure out what the graph of sine is. So I've got this xy axis. I want you to notice just how I've labeled my x-axis. I've been a little strategic with this to make it easier to graph. So I have just a handful of points that are going to help me graph sine of x on this xy axis. And I can use the unit circle to do this. So for instance, if I have x equals 0, so on my unit circle, so here's x equals 0, so this will equal 0. That's the value of sine there, right? Or what about pi over 4? So what if I go to pi over 4? So at pi over 4, I just pull out the y coordinate, right, to get the value of sine. So that'll be, here's my y coordinate, right? Here's the value of sine. What about pi over 2? So just one more time to do this. So at pi over 2, the y coordinate is 1. So in my table, I can fill in 1. And so I would encourage you just to take a second to quiz yourself to see how well you know the unit circle. So see if you can fill in the rest of this table just using what you know about the unit circle, and then you can hit play when you're ready. So here are the other values that I need. Okay, so I've created this set of points, and I'm going to just plot them on a graph like you've always done whenever you graph. So I've got 0 here, and then I've got this square root of 2 over 2, so maybe we don't know where to plot this one, so I just wanted to figure that out. I plugged it into a calculator. Just FYI, square root of 2 over 2 comes out to around 0.7, so you can just kind of, eyeball where you think that should be. So we're looking at pi over 4 and square root of 2 over 2, so pi over 4 is somewhere in between 0 and pi over 2. So let's see, I'll mark this for 1 and negative 1. So here's pi over 4, and then here's about 0.7. Okay, so that would be my square root of 2 over 2. And then let me just graph the rest of these points. So let's see, I've got pi over 2, 1. I've got pi 0. I've got 3 pi over 2, negative 1, and then I've got 2 pi and 0. So I've graphed everything out. So now I can show you what the graph of sine looks like. So it has this like wavy motion to it. Now, this does not really capture why sine is periodic. I've just drawn one period. You'll learn more about periods as we go along the video. But I've only drawn like one period of this sine wave. So what I want to do now is I want to manipulate this table. So here's what I'm going to do. What happens if I make all my x coordinates negative? Now you can take a look at the unit circle to help you figure this out, but I'll tell you what happens. So if I make all of these points negative, then all of my y coordinates end up becoming the opposite of what they were before. So they all switch signs. So you can see how I've switched this. So just to make this a little bit more clear now of what the graph of sine looks like, I'm going to go ahead and plot those points. So I went through and plotted them all. And now I can connect them. And so now you can see how sine is periodic, right? It has this clear repeating motion. And this is what we're going to really try to deconstruct as we are going through some of these videos. So as long as you can see the pattern, we're good to go. And now what I want to do is I want to pivot and I want to talk about cosine. And we can do the same things. So I've got the exact same points. So we're just going to kind of brute force our way to graph this. So I'll use the unit circle. So now, if I plug in 0, I know that cosine of 0 will be 1. So just using my unit circle, so I can plug that in. And then if I go to, pi over 4, that will be square root of 2 over 2. So if I plug in pi over 4, I get square root of 2 over 2. And once again, you can just continue this all the way down. So I would encourage you to pause the video and just see if you can fill in the rest of the table for the values of cosine. So here's the rest of my values here. And once again, I'm just going to go ahead and plot all of these points now on my new graph. So I'm going to plot those points as you see here. Now take your time to plot the points on your end. You'll see that they're a little bit different from how sine looked. And if I connect them together though, I still have kind of that wavy motion, right? So we see that. And once again, like this is one period that we're looking at here. So I want to show you how this graph has that repeating pattern. So I'm going to do the same trick that I did for sine, i.e. I'm going to now take the negatives of all of these. Now, here's what's interesting when I plug in all the negatives. Maybe you think, oh, now all these are going to change. That does not happen. All of these points, they all stay the same. They don't become negative. And you can look at the unit circle to confirm that for yourself. So if you plug in cosine of negative pi over 4, you still get square root of 2 over 2. Or if you plug in cosine of negative pi over 2, you'll get 0. So you can confirm this on your own using the unit circle. So all these y values actually stay the same. So now I'm going to go ahead and I'm going to plot all of these points onto my graph. So I'll go ahead and plot those as you see here. And then I can continue my graph. And now you can see how the graph also has its own repeating pattern. So the graphs of sine and cosine are pretty similar. And what I want to do is I want to just take a moment to notice some characteristics about these graphs. So I really want to dive into them a little bit. So first of all, the graph of sine, we have a special term for that wave. It's called a sine wave. I know it's not the most creative name, sine wave or sinusoid. So those are the two terms that we use to describe sine. And then cosine, so the graph of cosine, it really looks like sine, right? Except it's just been moved. So we think of, so if I compare the two, so here's the graph of sine, here's the graph of cosine. Let's look at that one more time. Graph of sine, graph of cosine. So it literally looks like I've just taken the graph of sine and moved it back, right? That's really what it looks like. And that's what we think of the graph of cosine. It's really the graph of sine just shifted pi over 2 units to the left. That's totally what it looks like when we compare them. Okay, so now what I want to do is I want to talk about a few other special terms. So we talked about period, and we're going to talk about that more in another video. But what we say for both of these is that the period of them is 2 pi, so meaning that the graph will repeat itself every 2 pi intervals. So we call the period of these 2 pi, and you can see that, right? So here is 0 to 2 pi. So I can see, right, here's another, so maybe I'll just be a little bit more clear. So from here to here, this is one period, 0 to 2 pi. This is a period that is 2 pi wide. And then this is another one that's 2 pi wide. And you can see how they're repeating one another. And if I were to continue this graph going this direction or this direction, they would continue to look like this. Now, if I compare that to cosine, it's the same thing. It's just a slightly different pattern that's repeating. So this block here and this block here, they literally are just a repeating pattern. And these patterns are 2 pi. You could think of it as like a 2 pi width, I guess, if you want to think of it that way or something. Okay, so let's talk about continuity. So where are these graphs continuous? So if you look at them, so the idea behind continuity is that I should just be able to trace it without ever picking up my pencil. So could I just continue to trace this wave, or could I continue to trace this wave and just go on forever without ever having to pick up my pencil? Yes, I can. So we say that the graphs are continuous everywhere. They really just keep going. So they're continuous from negative infinity to infinity. That's the mathematical way of saying everywhere. What are the domain and ranges of these functions? Okay, so if I look at the graph of sine, so I could just keep going with this pattern for forever. I could keep going in both directions. So I can see that the domain is all real numbers, but then look at the range. On the sine graph, the highest number it hits is 1, and the lowest number it hits is -1. And we know that also is true from the unit circle. And then if I compare that to cosine, it's the same thing, right? So all real numbers for the domain, I could just continue this pattern for forever. But the highest y value it'll ever hit is 1, and the lowest y value it ever hits is -1. So that actually will translate then to our domain and range. So the domain for both graphs is just all real numbers, negative infinity to infinity. And then the range for both graphs goes from -1 to 1, and -1 and 1 are included, so they get square brackets when we use our interval notation. Okay. Okay, so we've got domain and range for both graphs, and now let's talk about the x-intercepts of sine. So where do we notice that the graph crosses the x-axis? This has a pattern to it, okay? So look, hits here, -2 pi, here, -pi, 0, pi, 2 pi. So really, like any whole number value of pi, we have an x-intercept. That's where the sine graph is crossing. And so the way that we describe that then is that we say that the x-intercepts have the form n times pi, where n is any integer that you want. So it can be a positive number, it can be a negative number, it just has to be a whole number. Okay, what about the x-intercepts of cosine? Well, let's take a look. So now if I look at where this graph is crossing the x-axis, it's crossing here, 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 here. So this is -3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2. So these are really odd intervals of pi over 2, right? So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. So to represent that, we write this as, we say that the x-intercepts have the form 2n plus 1 times pi over 2, where this 2n plus 1, this is the general form of an odd integer. So if you plug in any number n into this formula, 2n plus 1, this will always give you an odd number. So if you plug in 2, you get 5. If you plug in 3, you get 7. So you can prove this to yourself. This is just how we indicate that it's got to be an odd integer. So an odd integer times pi over 2, that's the form of our x-intercepts. Okay, so the last thing I want to talk about is kind of the interesting behavior that I showed you when I made my coordinates negative for these two graphs. So there's what we call a test for even and odd functions. The test is very simple. You take f of negative x, meaning you just plug negative x into the function, and then there's really two results that you look for. If you plug in negative x and you get these values negative f of x, then we say that the function is odd. And if you plug in negative x and then you just get out the function itself, then we say that the function is even. So I'm going to show you how these actually look so that you understand this, because I know sometimes reading this, it's like, wait, what does this say? And by the way, if you don't get either one of these results, it's totally possible to get neither of these results. So when that happens, if you don't get one of these, then the function is just not even and it's not odd. That's it. Okay, so let's talk about odd functions for a moment. So odd functions. So like I said, f of negative x equals negative f of x. And so odd functions, these are functions that we say they are symmetric to the origin, which means that if you have the point AB, then you are guaranteed, if you have an odd function, to also have the point negative A, negative B. That's like part of the power of knowing that a function is odd. If you know you have this point, you are also guaranteed to have this other point. And then for even functions, just to take it a little farther, so again, that's the test for even functions, we say that these functions are symmetric to the y-axis. So what that means is if you have the point AB, then you'll also have the point negative AB. So you're guaranteed to have this point. If I know I have this point, I'm guaranteed to also have a point of this form. Okay, so my graph y equals sine of x, we actually discovered that that is odd. Okay, so remember, this is what makes an odd function odd. So let's look at this for a second. I make everything negative. I take the negative version of my coordinates, and then all of my y values should end up being negative. That's exactly what happened, right? So I turned each one of these into something negative, and I got the opposite sign out. So this literally is showing what it means to be an odd function. We got the opposite sign each time. So that's what we're looking for. And so we can really see that sine of x is odd by looking at the points and the graphs we were just kind of playing around with. And so we also have that, or one thing that we know will happen if I were to plug negative x into sine. So we haven't talked about this yet, at least in the class that I'm teaching, but what would happen, I can tell you what would happen. If I plugged in negative x, this would be what I get, negative sine of x. This is actually a trig rule. We'll talk about this at a later time in another video. Okay, so sine of x is odd. We saw it in the points. Cosine of x is also is even. So remember, to be even, so just to remind you one more time, just helping you wrap your head around this. So if I plug in negative x, it should do nothing to the function. It shouldn't change the function values. Well, that's also quite literally what we found, right? I plugged in negative values for my x's, so I changed these to all negative, and my y coordinates didn't change. So that's exactly what makes something even. So what we would expect to happen if I were to plug negative x into the function is I would get just cosine of x. This is what would happen to show that it's even. Again, you probably don't know this yet. We haven't discussed this, at least in my class. This is another trig rule, but this is something that's guaranteed to happen since it's an even function. And so that covers everything about just the basics of the graphs of sine and cosine. So I'm going to end the video here. So if you found that helpful, just consider hitting the like button or leaving a comment if you have a question or anything like that. I'm going to leave it here, and I'll talk more about these graphs in other videos.